The air around us is actually filled with microscopic particles that we usually can't see. So that's everything from tiny viruses and bacteria through fungal spores. Then there's also fragments of animals, bits of skin, hair. We use various spore-trapping devices to collect those particles, and then we can analyse them back in the lab. So this is really important for farmers because if they can get a heads up on when disease is expected, they can actually make decisions on whether to, for example, spray a fungicide or another crop protection product. Or if the crop is almost ready to be harvested, they might make a decision for vegetable or fruit crops, for example, to harvest the crop before the disease takes hold. Sometimes our information actually gives farmers the confidence to hold off spraying when they know it's not necessary, and that is better for the environment and it saves the farmer money.
So this is a rain shield that just pops off here and reveals the spore trap itself. Just pop that there. And what happens here is these two rods are spun round at very high speeds, which sucks in any air below. It sucks about 100 litres of air a minute, and then these two rods just pop off like this. And what we have here is a polythene rod that's covered in a thin layer of Vaseline, which will impact any sort of airborne particle, be that a spore, some pollen, or even small insects. And we can take these back to the lab and do subsequent analyses. And this is actually our most powerful spore sampler that we have today that sucks in over 200 litres of air a minute. And what you'll notice straight away is the weather vane at the top here, and that ensures that the air intake is facing the direction of the wind. So now I'm going to open it up and we can have a look inside. So the way that the sampler works is that air is taken in through this inlet here, and it's forced through this black column, and the air is actually vortexed through the column, something that you'd see like in a vacuum cleaner. And then the air is deposited in these tubes here. And because it's already in a tube, it really speeds up our downstream analyses back in the lab.
My role is to process the air samples as they come off the spore traps, collecting the DNA to determine accurately the amount of fungal pathogen in the air samples. Each fungal pathogen has a unique DNA sequence which we can then target and amplify, getting results more rapidly and more specifically than traditional microscopy methods.
Once we get our sample in, we extract the DNA from it and we amplify a particular region of the DNA called a barcoding gene. That barcoding gene differs between our different target species so that we can investigate which one is which. We then use that amplified DNA to prepare DNA libraries, and those DNA libraries we then sequence to investigate what species are present in that sample.
We're currently working on a lab-in-a-box system that will do a diagnostic test in the evening after it's done a period of sampling and actually text the results out to the grower. In the next 10 years, I can see more automation happening, and I think we will actually start to see DNA sequencing start to become a mainstream normal method for analysis. The reason that's very good is because we get information on hundreds of different target organisms in one go, and so it can be very useful not only for warning against crop diseases, but it can also be useful for monitoring biodiversity, for example, as well.